Hello YouTube, this is my third video in my module on sketching systems of inequalities, in which we are going to focus on two special cases, the first one being the no solutions case, and then the second one being a feasible region that we say is unbounded, and where we look for vertices on those. Okay, so we're going to start with the no solution case. Actually, I'll come out and say this. But what does it look like? Well, one could think about this. When you graph a system of equations or inequalities, you're looking for points that are common to all graphs in the system. And so if you had a no solutions case, this would be a graph that when we graph these and shade them, they will never never intersect, okay, never overlap at all. The feasible region would be null. Okay, so we'll go ahead and start with this first constraint here. We say x plus y is greater than 3. We're going to graph this as if it were x plus y equals 3. Graph the boundary line here. And so we could say, well, an easy way to do this, we could find intercepts. We could find the x and y intercept. So if we plug in 0 for x and 0 for y, respectively, plugging in 0 for x yields this equation y equals 3, or the solution y equals 3. So we say when x is 0, y is 3. And when you plug in 0 for y, you get x is 3. So we get 3 here. So it hits our x-axis at 3 and our y-axis at 3. So, we'll go 1, 2, 3 to the right. Also 3 up, and then connect these dots and label it. We're going to connect these with a dotted or dashed line. Okay, so we say dash, 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 dash. Reason being is because it wasn't a greater than or equal to situation. It is a less than or greater than situation, no or equal to. We're going to label this x plus y equals 3. So here's our graph here. We'll take a look at the second constraint here, that is x plus y is less than negative 1. So we get x plus y equals negative 1 would be the graph. We'll graph first here. We end up with this. We say, well, an x-intercept, if I plug in 0 for y, I get negative 1 for my y value here. Suppose we could put that there in that color. We say plugging in 0 for x, when we plug in 0 for x, we get y is negative 1 as well. So we get our intercepts here, negative 1 comma 0, and then 0 comma negative 1. And so you can see that in this instance our lines are parallel. This one would also be a dashed line because it is just a less than case, not a less than or equal to. So we'll go ahead and finish graphing this here and label it. So we get this x plus y equals negative 1. So in terms of shading, we say, well, which way do we shade? Well, we need to test a point that is on not on the constraint that we're trying to shade. So I noticed that 0, 0 is actually a good potential point here, easy to test, and it's on neither of these constraints. So if I were to plug, say 0, 0 back into the first constraint here, we get this. We say, all right, so 0 plus 0 greater than 3. So 0 plus 0 is greater than 3. So 0 is greater than 3. This, of course, is false. 0 is not greater than 3. So we are going to, with this constraint here, see, I labeled it. I knew it was this one. Since 0, 0 is false, we're going to shade away from 0, 0 to the side containing all the points that are not on the same side as the point 0, 0. Now the next constraint here, if we were to plug in 0, 0 into it, we get the statement 0 plus 0 is less than negative 1. So we get 0 plus 0 is less than negative 1. And 0 less than negative 1, this is also a false statement. So since it's false, I am also going to shade away from the side of this constraint containing the point 0, 0. So that'd be all these points over here. So what you see is this. We've shaded a couple half regions of the entire plane here, but there are no points that both of these inequalities would share simultaneously. So the feasible region, there's no feasible region. It's a no feasible region is one way to kind of interpret this. And since there are no points that are feasible for everybody, we could say no solution. No solution. And of course the fancy term for this is it's an inconsistent system. Inconsistent system of linear inequalities in this case. Okay, so we're going to do one more quick system here in which the feasible region is unbounded. What would an unbounded feasible region look like? So go ahead, graph these out. We'll do a little bit quicker this time. We'd say on my first constraint here, x plus y is less than 3. Say x plus y equals 3 is what we would graph. And so this has x and y intercepts of 3, again, just like on our last example we just did here. And it is also a dotted line, so we'll go ahead and put in this dotted dashed constraint here and label it with its associated equation. So x plus y equals 3. And then we'll go ahead and graph the second constraint here, which is x plus 2y equals 3. So we say, okay, well, what are my intercepts? We notice here that if you were to plug in 0 for y, you get an x-intercept of 3. So this also shares a common x-intercept right here. And we say, okay, so if 2y, if you were to plug in 0 for x here, you get 2y equals 3. So y is 3 halves, or 1.5. Okay, so we'd say, well, it would hit right here. Okay, and so we'd say this is a dashed line. So to the best of my ability here, I'll draw on this dashed line. that is our boundary line here. And I'm also going to label this one with its associated equation, x plus 2y equals 3. So now, of course, is the point in the situation here when you're graphing a system, which you go back and shade. You say, well, which point could I test? Well, 0, 0, if I can. You don't always test 0, 0. If 0, 0 was on one of these constraints, we wouldn't test it. But since it's not, we can go ahead and test 0, 0 and say, does it make this constraint true? So plugging back into the original situations here, we say x plus y less than 3. If we plugged in 0, we get 0. 0, 0, we'd get 0 plus 0 is less than 3, or 0 is less than 3, and this is true. And so this would belong to the first constraint here, which we labeled was this bottom one here. Since 0, 0 makes it true, we would shade this way, toward 0, 0. We'll put in all of our arrows here. We say, okay, well, let's test 0, 0, my second constraint. Up here we'd say you get 0 plus 2 times 0 is greater than 3. In other words, I get 0 is greater than 3. And this is not true. This is not a true statement. It's false. And so since it's false with our second constraint here, which is this one I took the time to label right here, we would shade away from the point containing 0, 0. So we'd say it'd be all these points right here. What we are looking for, of course, is the feasible region. The region containing all the points that would make all of the inequalities in the system true. And we notice that it's this kind of triangular region up here. The thing about this region in this instance is that it would continue to go on indefinitely. So we refer to this feasible region as an unbounded feasible region. And not only is it unbounded, does it have vertices still? I mean, like, does it count as a vertex if you have a point where, there's a cusp here like this? We say it indeed does have a vertex at this point here. We say, well, what is this vertex here? We're still always interested in finding vertices. And we say clearly this point here in this instance is 3, 0. 3, 0. And of course, if we weren't sure, what we could do is we could always solve a system with the two equations that are meeting at this point. So if I wanted to solve this system here, we could do like, elimination method. We could take the whole top equation times a -1. We'd end up with this new system, x minus y equals -3, and x plus 2y equals 3. And when we sum these, we get y equals 0. And since y equals 0, we could go ahead and reinsert this back into any of the original equations. What if I did this here? We say x plus 2 times 0 equals 3. We get x equals 3. So we get this point 3, 0, which of course corresponds directly to this. Try this again here. This point here, this vertex point here. But this would be the only vertex of the feasible region. You'd see it would just be unbounded in the upper left direction. Cheers.